Now, our discussion of integration by parts wouldn't be complete without addressing somehow how we deal with definite integrals in integration by parts. And so I have the problem here, integral from 0 to pi over 2 of x cosine x dx. And we're going to start out as normal, choosing a u, and that would be x, and a dv, and that would be cosine x dx. We're going to differentiate as we normally do. Du is dx, and v is sine x. And so now when we put it all together, we have uv, which is x sine x, minus the integral. Now let me just first state the proper way to go about this would be to put that x sine x in brackets from 0 to pi over 2, which means we're going to evaluate x sine x at pi over 2 minus x sine x at 0. Now we still have an integral here, and that would be the integral from 0 to pi over 2 of v du, which is just sine x dx. So if we wanted to do all the subtracting at a later time, we can just rewrite the bracket x sine x from 0 to pi over 2, or we could plug in here. It's going to be simple. The second one, 0 times sine of 0, will just be 0. So we'll have pi over 2 times sine of pi over 2, which is 1. And so that whole first thing will just leave us with pi over 2. Then minus the integral of sine x is negative cosine of x. And I'll bring out the negative and make this positive. And so we'll have pi over 2 plus cosine of x evaluated at pi over 2 minus cosine of x evaluated at 0. And that, cosine of pi over 2 is 0, and cosine of 0 is 1. And so we'll end up with pi over 2 minus 1. And pi over 2, roughly 1.57 minus 1 would be about 5.7. Sorry, 0.57. But if we wanted to do this on a graphing calculator, we could get a much more precise answer to that. But for now, or a better approximation, I should say, the precise answer is pi over 2 minus 1. Now you could also, with this, you could do the whole thing out. That is, after we found the antiderivative of sine x to be negative cosine x, and we could have put x sine x plus cosine x all from 0 to pi over 2. And you should see when you do that, you're going to get pi over 2, as we did above for the x sine x, times 1, and the cosine of pi over 2 would just be 0. So we've evaluated that whole expression at pi over 2. Now we'll evaluate it all at 0, and x sine x at 0 will come out to be 0, then plus cosine of 0 is 1. And you'll see when you do it that way, you also get pi over 2 minus 1. So really either of those two strategies will work when using definite integrals. And I'll give you one to try here. Now you should note that really all of the different types of or variations of integration by parts could become definite integrals. And so you really, we've only shown one, and I'll show another one now, but there could be many different varieties of this, so you really need to practice more. But I think you'll have the basis, the basic technique in order to accomplish any of those. So let me give you the integral from 1 to 2 of x squared ln of x dx and see if you can work that out. So you can stop the video and come back and take a look at the solution. Okay then, for this problem we have x squared and ln of x. According to Lippitt, logarithmic comes before polynomial. So u is equal to ln of x and dv is equal to x squared dx. We'll find the differential and the integral. Du is 1 over x dx, and v is equal to 1/3 x cubed. We put it together, so we get uv, which is 1/3 x cubed ln x, minus the integral of v du, and that is the integral of 1/3 x cubed times 1 over x dx. Again, technically we should put our limits of integration around both of those, and then we're still going to evaluate the integral. And simplifying for the integral, we're going to get 1/3 integral x squared dx from 1 to 2, and we'll integrate. So we have 1/3 x cubed ln x at 2 minus 1/3 x cubed ln x at 1. Then minus 1/3 times 1/3 x cubed from 1 to 2. And for time's sake, I just give the final answer 8/3 ln 2 minus 7/9. And you can pause and follow that work.